Thanks for tuning in today. I'm Dr. Nick, the Incrementalist. Join me as I seek out the small incremental changes being applied in other industries that we can learn from and that can be applied in healthcare. Can these changes bring immediate value, but also add up to the big improvements and revolution we need in healthcare? Come along with me to explore the possibilities. My innovative guests from around the globe have used small incremental improvements to achieve their moonshot. And today, I'm delighted to be joined by Kathleen Griggs. She is the president and founder of Data Buoy, or as we say in England, Data Buoy. Kathleen, thanks for joining me today.
Well, thank you, Nick. I'm very happy to be on the show today.
Tell the listeners a little bit about your background. You have this really storied history of technology innovation that's arrived at this point of Data Buoy and some of the technology that you're rolling out. But help us understand how you got here and what your background is.
Well, my background has been in defense research, and I've been a long time either as a government civilian or contractor, or both sides of the world. My whole entire career has pretty much been Department of Defense research and development. The origin of Data Buoy and the technology here, it really just goes back to the Defense Advanced Research Projects Agency, or DARPA. I'm one of those lucky people that got to be, a moth flying around DARPA. I was a DARPA agent, I was a DARPA contractor, and DARPA is a wonderful place where you get some of the greatest minds, that coming together, thinking about the future, right? And imagining that you have the ability to go after a technology that DARPA assumes 90% of these they're willing to accept a 90% failure rate. So you can go out there and do a high risk program and see if you can make this idea work. And 10% of the time it does. And then, so imagine, what a great environment it was, is to try to solve problems that warfighters had, and that actually ended up benefiting, other people too. And be in that environment and see throw some ideas out there, DARPA puts money on it, see what sticks. So the original technology that started Data Buoy was a DARPA program. It was a program that started in the early 2000s. It's a technology that I think it didn't stick, and we're going to, maybe you'll have a follow-up question on that. It didn't necessarily benefit the intended target, which was the warfighter, but it really does have applications in the civilian world. And so for that, it was a great technology.
So I think, an interesting point, and I hear this repeatedly on this show, and it's one of the things that I like to highlight in terms of innovation and those steps. And what you're reaffirming is something that I've heard repeatedly, which is no matter what your idea is in the first instance, it should be, as one of my guests described it, a sacrificial lamb. The idea that it's going to be successful is just founded in falsehoods, as you've just refined. I mean, 90%, that's a huge proportion. So you have to be willing to sort of discard it. In this instance, you say it wasn't a success. So tell us a little bit more about that.
Yeah, it's funny because people think that just because we have the idea and we can engineer it, that it is going to be a success, even if it does work. But the issue with the military is that they have to go out and fight a war, bringing all their infrastructure with them. And to add infrastructure into a military tactical environment, it's a big hill to climb, depending on what you're looking for, right? I can go into all the programs, we talk about satellites and things that go overhead and comms, and, there are definitely ways that you can create more and more infrastructure to support your warfighters. But this particular program, which was a sensor network program, I think the infrastructure requirements at that point weren't necessarily considered. And that's because the first part of that program was to discover how can we build these sensor networks? Can we make these work? And then it got to the final question of, well, geez, these things, what really happened is that the goal of the program was to create 10,000 sensors that would mesh together and perform some task. And while the sensors could do that task, what was a killer was the fact that it took too long to change batteries, right? They just didn't have time to change the batteries on these things. And you can't imagine going to war and putting these things out there and having to run out every other day and continuously change batteries on this. And so that turned out to be, I think, one of the real limiting applications is soldiers having to carry batteries for this stuff. And it stymied, I think, the the acceptance of, and there's a couple of other technical features that do require care and feeding infrastructure that really prohibited, I think, a broad acceptance of our particular technology, which was this acoustic localization sensor.
Just fascinating, down to that sort of very simple issue that, caused challenges. But help everybody understand, what is it that we're talking about? So what is it that Data Buoy is? I think, the history of the name actually lends a little bit of insight to this. And what is it that you've done with it through that program to develop it?
So the history of the name Data Buoy is a nod to my Navy career as a Navy civilian. I actually worked for the Naval Air Systems Command at one point in time, and the Data Buoy contract, the original contract that I received, was a small business tech transfer contract. So it was a small business startup, and the whole goal of that program is to create an opportunity for a small business to mature a developing technology. And our teammate was a Vanderbilt University, and they had the DARPA program. They were developing this acoustic sensor net. And that was a Navy contract. It was awarded initially by the Office of Naval Research. So what do you call unattended sensors that are going to sit in your environment and collect data and then assist you, right, as you move through it? And so we were imagining that this is a data buoy, as like they have data buoys in the ocean that provide, navigational information for boats that are passing by, that they sit out there and they measure the environment, they give that information back as you go through the network. So the idea is to take that concept and have these sensors sit on land. And so that was the origin, is that these are generic unattended sensors that are persisting in your environment, sensing, and they're going to provide users with information.
So extending that a little bit further to understand it. So when you say sensors, what are they sensing? What are the elements? What are the data inputs to that? And what are you trying to achieve with that network?
So this is an acoustic sensor network. And, we were initially thinking that we were going to move beyond acoustics. And I think we've still been in the world of acoustics ever since. Funny thing, so that the early DARPA program was a sensor mesh program. It was basically a communications middleware. And what the acoustic sensor network initially achieved was a way to demonstrate really accurate time synchronization on these low power sensors that were out. So time synchronization is that you have 3 or 4 sensors in the environment. They all hear a signal and they talk to each other, and they all decide at a very accurate timing standpoint, when did they hear it? Mm-hmm. And then they can collaborate, and then they can localize on that event. So what this is that if they have very accurate timing that multiple sensors can hear an event, then you can reconstruct when and where that event happened. What we end up with is a sensor network that can very accurately localize on an acoustic sound and an acoustic event.
So, for intrigue as much as anything, I mean, the science sounds very similar to GPS technology, which is based on time. What reference base, what degree of accuracy for that time is necessary for this that you're talking about?
So you're exactly right about that, and the math is impossible. And don't ask me to go into it. I'm going to bring someone else on if we have questions about how, and it's, that we're not talking in terms of the accuracy of the location accuracy. For us, for acoustics, it's really just a few, it's less than a meter, a few tens of centimeters maybe. And however, that's about as accurate as you can get, because imagine our sensors are little, each one of our sensors is a little array. And I don't know if your audience can't see this, but
so it just looks like a Wi-Fi block.
It does.
A base station, as an example.
Yeah, but look, the microphone separation is very much like the distance between your ears. So these are one of these things. Elephants obviously have bigger ears, bigger separation, but for the scale of the environment we're in, it turns out that this separation in this acoustic range is about what you need for getting good localization. So that's
fantastic. So you took the concept, in the DARPA program, not successful for some of the, basic principles of care and feeding, as you described it, but that's now moved into a new program that you're essentially offering. Tell us a little bit about that.
we are primarily a gunshot localization sensor. The product is called ShotPoint, and so a gunshot is a very, very distinct, and time-wise, it's a very sharp event. So it's easy to detect, it's easy to localize. I don't want to say easy, you can get it wrong, but it is a very distinct event. And we've spent lots and lots of time, quite a lot of bullets have been fired to characterizing gunshots in various environments. But that is the primary product. The idea is that when you put this sensor network into your building or outside, if anyone fires a gun, we're going to get a location. We're going to publish that location in a second. And in that second, you're going to be able to do a lot of things with that. You're going to cue cameras. You're going to write messages to people. Right. You're going to create response.
It reminds me a lot in terms of the sort of principles underlying this. We see this in US sports. It's started to permeate into the British sports and the Barclays Premier League, which is soccer. And they've introduced a new VAR, as they call it, the video assistant referee, where they go back and review. And they have a goal detector that the referee wears a watch, and it gives him an indicator of whether the ball passed the line or not. And my sense of the sort of utility of this is that if you have this network, you could essentially feed that information into almost instantaneously. You're saying within a second, that's as close to instantaneously, both sort of I imagine not just the location, but also the characteristics. Can you detect the type of noise, the type of caliber of the weapon, and so forth?
Yes, and I think you bring up a really good point, and that watching a ball penetrate a goal line, right, is something that a camera could do really well. Machines are better than people at this. That's just the way it is. You can program a network to respond and send messages when it sees the right signal, and you can do that very reliably. And they never get tired, and they're always right, and they always give you the information you need right then. And so why not take advantage of the computers that we have and the hardware that we have to give that information out when it's just so much easier for, as long as it's economical, as long as people are willing to accept the help, then why not put it in? That's my philosophy. Why not use that data?
Right. And what's the density of sensors necessary to get this kind of accuracy? So you talk about buildings, but I sort of think about this in broader terms. And, I know you had a specific example with the tragedy that took place in Las Vegas. You sort of described some of the capabilities of this. Tell us a little bit about what would have been required in that instance to have gotten to the accuracy and level of information for the location of that shooter.
That's another great example of why machines are so good at this. So in the Las Vegas example, that's an example of where there's a shooter who was about 400 meters away from this event, and he's shooting a rifle, and that rifle is supersonic. The rifle bullet is supersonic by definition, and rifle bullets can be supersonic anywhere from 600 meters to 1,500 meters sometimes and beyond, depending on what type of rifle you have. So that bullet is traveling. And supersonic, pardon me if I'm getting too technical, but a supersonic bullet is actually propagating its own shockwave, right? You can imagine that thing is. So that's a very distinct signal. So it takes 3 of our sensors to be able to pick up that signal to create a line, to know where the path of that bullet. And that happens instantly. And so for every shot, if our sensor network were around that event venue, then every shot that went by that network, we would be showing a line. And that line is about a degree angle accuracy. We would have had that hotel room every time that shooter shot a shot. And so that would have saved, with 3 sensors. And we need 3 sensors to make a line.
Right.
But any 3 sensors would have, that could have heard that. And so the question is, how far away do these sensors have to be from that bullet to pick it up?
Yep.
So we have a standard where for our system, our standard is we have 50-meter spacing. That's 165 feet. And with that kind of a spacing, we're able to pick up 22 caliber, which would be the weakest gun signal, and then everything else above that is gravy. It's easy. So, but that's our minimum. We know that we're going to get enough information from the acoustic signal to make that automated determination with that sensor spacing. And so that's how our system is designed. And again, from then on, it's a machine. It just does what it does.
So I mean, that's fascinating. And I think the important thing there was when you talked about the supersonic, I immediately think of Concorde and, some of the pictures that we've seen, that, propagation of that wave. I think what you were describing with the 22 caliber, because that's the lowest sound.
22, yes. Mm-hmm.
Yeah.
And that's a subsonic pistol, by the way. So that's okay. Go ahead.
So lower. So you would need to be closer to it. So that 600 to 1500 meters is how far away you can detect. Am I understanding?
Oh, no,
that?
I actually mixed apples and oranges here. Okay. So so when you have a subsonic weapon like a pistol, right, that's going to have a muzzle blast, but the actual bullet is traveling slower than the speed of sound. So we're not listening to the bullet in that case. We're just picking up the location of where that shot happened.
Right.
But when you have a rifle, there's two signals that happen. One is you still get a muzzle blast off that rifle, but the bullet itself is also, because it's supersonic, it's creating this shockwave boom when it flies. We're picking that shockwave off the bullet, so we can see both. We can see the muzzle blast, and in that case, we can also see that bullet
and the trajectory, right?
And then therefore the trajectory, because that bullet is moving through space being really loud.
Right.
So that's why we're getting that.
Fascinating. So for those of you just joining, I'm Dr. Nick, the Incrementalist, and today I'm talking to Kathleen Griggs, the president and founder of Data Buoy. We're talking about their shot detection system and the elements that are required, essentially a minimum of 3 sensors placed to be able to co-locate, and then for each and every signal, you're able to draw a line that is within 1 degree of accuracy. So, and almost instantaneously. You talk about a second, but as close as anything to instantaneous. So tell us a little bit about where this is going inside. So in buildings, and the ongoing innovation that you've got, and the ability to put this in other places, not just in public spaces.
So we are, we're hoping to bring more and more of these in buildings, and inside, it's a different environment from outside. One thing I didn't talk about on the technical side are all the echoes and bounces and things. When you have loud shots, you get a lot of bounces. So we have a particular, because we're a sensor network, and it's a patented approach where we actually use information from multiple sensors to recreate the actual source, to know exactly where the source of that original sound came from. And then we eliminate all of the echoes and bounces and things, because I like to say that in about 30 seconds, everybody knows there's a shooting in this school. The question is where, right? You really want to know exactly where that shooter is. And so that's where we excel. I think we're actually kind of unique in our ability to throw out those echoes and decide where that shooter is. We have that shooter's position instantly. All these institutions have tons of surveillance cameras already deployed. So we take the nearest camera and we grab that image from the exact moment of the shot. Yep. And this way we have a little tool that we do a pre and post, a couple of seconds of images just before and after the shot, because there's a chance that shooter might have walked out of that field of view. You get a couple seconds before and after, and you go, oh, there, I can see that shooter. So that's the information you need to know, and you want that, we call it the Kodak moment, with the gun in that hand. You know exactly who the shooter is. So you've got the crime, you've got the suspect, you've got everything you need, and that shooter, the description of that shooter is what the responders need. They want to know it's the person in the black pants and white shirt. They need that information, because they need to know how many shooters there are. They need to know who they are, and then where to find them. And then, obviously more information than that we can. So by solving all of that problem up front, indoors and outdoors, for us, it doesn't matter. We'll do both, and we can go, you can subscribe, you can put sensors indoors and outdoors, it'll all be on the same network, and you just get that information. So in terms of who's using it, that's a whole nother question. Would you like me to go on, and I can give you a little bit of my thoughts on that as well, because it's a new technology. And
so I think there's, a clear path for this, and, the value add in terms of being able to identify, locate. I love that sort of capacity to tie the time stamp to geolocation of that sensor so that you have the images and you can then propagate that. How's it being used? Where's it in use?
So this is a technology that's not like a smoke detector, right? There are no mandates. There's no state law that says construction code that says you have to put these in. This is being installed by choice. So these are users who simply see the value in having this information, and they make their decision that they want to use this. And the choice usually involves some collaboration or some discussion with the local authorities or the police department, because it's much like if you install the smoke detector and the fire department can't answer, right? So this is so these are forward-thinking. These are progressive police departments that are working with the school systems or working with a commercial property that have security managers that know what to do. And these are generally individual and sometimes private decisions because they don't want to have to deal with this, with the potential for what could be a really terrible disaster. So in
the last couple of minutes that we've got, I know you've had some thoughts about this application. It's got much broader than this, and obviously, that's a key opportunity for the current challenges we face. But what else can you listen for? And as we think about health challenges, what are the other things and the other areas that we can, sort of think about?
So we like to think of ourselves as a generic platform, and our acoustic sensors can be used for picking up other signals, although we don't do voice recognition. But we do offer the opportunity that if whoever installed that system wants to run a particular exploitation tool, we want to be the lettuce on the sandwich. We want to support those applications, and so we provide a very nice acoustic signal. We provide information about where that signal came from, and we have this nice tie-in with the imagery. We have a number of generic things that we pull out of our sensors as they are right now. We have things called a bang, right? So what's really important is knowing what's not a shot. We heard something loud, it was sharp, and we'll send that information out, and we don't send a big alarm. We say it's a bang, it's a nice yellow signal, and the security manager might want to look to see that someone's doing construction in that area. Or we have something called a ruckus, which is an episode. So someone is, crying or screaming, or you don't know what's going on, right? That person, it could be somebody who's fallen or is in pain, or we don't know. But we know that this is abnormal, and we're going to send that information. We can send environmental noise information, and and there's all kinds of uses. So you could have a sound that comes, like I think mentioned before, in close proximity to that microphone. That sound could be even, like we talked about, a wings batting off of a hummingbird or a mosquito, and you could recognize that. And as long as you can get that signal out and into the right application, then intelligent people can write ways to make that signal to find benefit from that signal.
Fantastic. So unfortunately, as usual, we've run out of time. I think just extraordinary use of technology that's developed over time, and what's really intriguing about that additional sound, I think, you mentioned mosquitoes and the ability to differentiate between male and female mosquitoes based on their wings. Truly just great insights. And I love the concept of this and the potential for this in the future. Kathleen, it's been a great pleasure talking to you. Thanks for joining me today.
Well, thank you for having me on your show. I enjoyed it.
Thanks for joining me today. Do you have any better ideas, or have you found a small incremental change that's brought about a big improvement in your world? Let's continue the conversation on our hashtag, The Incrementalist, or share with me at DrNick1 on Twitter. You can find more information about the show on our program page at healthcarenowradio.com. And tune in next time to hear my discussions with leaders and innovators from around the globe who've revolutionized their space by using small incremental improvements to achieve their moonshot. I'm Dr. Nick, the Incrementalist, and I'm starting a revolution through evolution.